Our next legend is Charles O'Melia. Charlie is at Johns Hopkins University, recently emeriti there, and I think this talk follows well on the heels of Gary Sposito's. Charlie has performed research that yielded the principal guiding concepts of water coagulation, flocculation, and filtration, going well beyond, I would say, much beyond the DLVO theory that we heard earlier about, to looking at the surface coordination chemistry which controls these phenomena, unrecognized really before his seminal research. Charlie is a member of the National Academy of Engineering. His awards are so many, including the Clarke Prize for Water. He's also received many awards from the American Chemical Society, AEASP, and the American Water Works Association. I think one of the things for me that is most impressive about Charlie O'Melia is what a great mentor he is. Perhaps the finest mentor example of anybody, at least in the United States. He has many, many students who are professors throughout the world, including here in the United States. They all love him and speak highly of him, and nobody says anything negative about Charlie O'Melia. And to be able to have made such an impact on the field and still to have people think of you in that way is really something exceptional, I believe. So please join me in welcoming Professor Charles O'Melia.
Thanks, Charlie. I recently went to the hospital for a sleep study where they hook you up to many different things, and I think I'm returning to it as I stand up here. I didn't put much history in my talk, and so maybe I'll talk a little bit about myself. I tend not to talk about myself very much, but perhaps I'll start off that way. I was born in New York City, where we don't have any soil or trees or whatever. And I like tall buildings and I like concrete. I mean, what's this guy in environmental? And I went to school to become a civil engineer because I thought those bridges that I could see and the tunnels I went through and the tall buildings were man's finest achievement. Well, I think they're really quite an achievement, but I've been modified a little bit. So I studied civil engineering, and after 2 years, I made a mistake. I decided that this is all very simple, all these structure stuff.
Just quite higher, because it's not going to the back of the room. There.
Okay, can you hear me now? Thank you, guys. I took a course as a junior in something called sanitary engineering from a gentleman who was also a member of the National Academy of Engineering, Don O'Connor, and he's a mathematical modeler, and he got me interested in water and in dead fish that I could see in the Hudson and what some young kid could try to do about it. So I decided to become a sanitary engineer. I also spent some time every day of the year, including Christmas, playing basketball because I really wanted to be a basketball player. And it took me a long time to find out that I wasn't any good. I was too slow and couldn't jump. And so but by the time I graduated from college, I could see that the Knickerbockers were not chasing after me. And so I thought I'd go to graduate school. So I went to see Don O'Connor and said, "Where should I go?" And he said, "Charlie, I don't think you can make it at Harvard. Why don't you go to Michigan?" Well, it turns out at Michigan was Jim Morgan, who was also a Manhattan College graduate and who I actually played basketball with at Manhattan College. Yeah, basketball, Michigan, you know. So I went out and got my master's at Michigan in sanitary engineering with a really good engineering professor. And I also got a PhD from there. Jim left and went to Illinois and then to Harvard. I took my first teaching job at Georgia Tech, where there were some issues. It's quite a remarkable institution in my view, and it has lots of good students. But the fellow that was in charge of the environmental engineering or sanitary engineering section, was not a good guy to work for. And so I started trying to think of something else to do. I thought maybe I'll go to work for Dow Chemical because I had a lot of respect for them being from Michigan. But then one day I get this phone call from this German accent, turns out Swiss German accent from Harvard, asking me if I'd like to go there on a postdoc. I never heard of Werner Stone. And so I thought, well, I'm sort of interested in going in, and leaving here. Why don't I at least talk to this guy? He came down to Georgia Tech. He talked to me about what I might do at Harvard. It turns out he'd read a grant application that I had written when I was looking for funds. And so he invited me up to Harvard, and that's when I became an environmental engineer, chemist in the true sense of the word. I am an engineer. I'm not a chemist. You'll tell from this talk that I'm here under false pretenses, actually. Okay, so that's a little bit about my background. This is the title of the talk is Aquasols and Aquafaces. Aquasols, because I was greatly influenced by Sheldon Freeland when he was at Caltech, who really introduced me to aerosols. And I thought, well, aerosols, air, it's not really water. Werner has told me it's not water chemistry, it's aquatic chemistry, so we'll call these things aquasols. But then I became interested not so much in their surface coordination reactions or in the speciation at the surface, as in what impacted their colloidal stability, because that impacted their size and the distribution in the environment, sort of engineering things. And so I call the interface at the at the solid water interface, I call it an aquaface. This is the second picture, or maybe the second or third picture you've seen of Werner, and Jerry might recognize this. Werner wanted everybody to use a pH meter, but not much else analytically, I think. And he got interested in acid rain and weathering, and so he started a small project that went on over a few years in the Italian Alps in southern Switzerland. And there were a few small lakes in series, and he got some samples of the snow to characterize the rain, and then took samples out of these lakes in series to look at the weathering of the rocks. This is the famous, or maybe infamous, Lake Crystalline. That's how big it is. It's maybe, if you take Werner and put him on end about 10 times, you'll have the size of the lake. I would tend to wander over to Switzerland as often as I could, often in the summertime. It's not a bad time to go to Switzerland. And I showed up one time around the 1st of July, and Werner said, "You need boots." I said, well, you know, I've got shoes on. What do I need boots for? We never go out in the field. Well, it turns out that the group that had gone out a couple of weeks earlier to get the samples to measure alkalinity and calcium and things like that, and pH, some fog had come up, and they couldn't see where they were walking, and they got lost, and they drank the water samples before they got down. So they needed a second set of water samples, and so I was impressed into service and went out and was part of the group that got the water sample. Well, Jerry actually wrote some of the papers about this. That was my major contribution, was carrying water samples. This is another Swiss picture. Werner organized these conferences every few years, of which Gary talked about a little. And Jim and I think, went to all of them. And this was at a monastery, as I recall. And so this is the picture I selected of Jim Morgan. You'll see that he and I, well, we come from the same college and even the same master's degree. We tend to dress a little bit differently. Neither one of us maybe is particularly formal, though. Jim is clearly a legend in environmental chemistry. Werner is, in my view, the father of environmental aquatic chemistry. and in my biased view, the best environmental chemist there ever was. And if he was not deceased, I think he would be up here. That's my little attempt at history. I didn't plan that, but Gary sort of inspired me to say a few words about myself. See, Alan Stone is here. Alan has told me that every talk I ever give, I show something like this with a collector and some particles wandering around. I couldn't find the one I always use, and I found this old one. We did this in the late 60s, and I'm not going to talk about this at all today. Okay. It could be that I'm here today because of this early work, but I'm not going to talk about it. I've been interested in aggregation and settling in natural aquatic systems, lakes, reservoirs, the ocean, and also in the passage of colloids through groundwater aquifers. And this is maybe one of the reasons why one should think about it. You can probably see that this is the Nile River, this is the Nile Delta. It really has two main tributaries, so-called Blue Nile, which drains mountainous areas in Ethiopia and has a lot of clays. I don't know if I can say soils. Yeah, it must be soils. And also, there's a White Nile, which drains the equatorial region. This is Lake Victoria, and it's high in organic matter. And so for thousands of years, this organic matter and this clay soil drained down, met at Khartoum, and went northward to the Mediterranean. It formed a fertile Nile Delta. Prior to that time, there really wasn't much agriculture. With this fertile delta formed, civilization changed, and we became an agricultural civilization because of the aggregation of aquasols. Is one way to look at it. Okay, I gave a talk at a Gordon conference recently with the same title, and I emphasized the inorganic part of this in that one, and I'm going to emphasize a little bit more the organic part here, but there is a fair amount of overlap. And so for those of you that saw the Gordon conference, you're going to get some of it again. These are some data of particle size distributions in a variety of freshwaters, rivers, lakes, and also Rhine River sediments. This is particle concentration in number per liter, and this is particle size. And what this is, I picked this point, it says that there's about 10 to the 14th particles in these samples, larger than about 20 nanometers in diameter or 10 nanometers in radius. So 10 to the 14th is a number that we're going to pick up in a couple of minutes. That's a lot of particles. This is, my understanding is the Swiss have, is Rene here? A certain number of nuclear reactors, I think about 5. They had a vote and banned the possibility of any more, but they have nuclear waste. And so they wonder where to put it. They typically send it to France, but they're looking for some places underground to find it. And one of them was this Grinsel Aquifer, which is near Interlaken. It goes down, I think, several hundred to 1,000 meters. And so some samples were taken of the fluids in the aquifer. Okay, again, this is particle concentration, number per liter, particle size. This is 20 nanometers in diameter, and we have about 10 to the 13th particles per liter that are larger than 20 nanometers. Again, it's a lot of particles. Here's some old data from the ocean. These are 10 to the 8th particles per ml, so this is about 10 to the 9th particles per cubic centimeter, or 10 to the 12th particles per liter. That's a fair amount of particles. And this is just simple calculation based on the work of Smolakowski, Brownian kinetics. Second order reaction, you can calculate a half-time. A half-time is about 2 times 10 to the 11th divided by the number concentration. Half-time in seconds, number concentration per cubic centimeter. So these are my 3 locations. The surface waters, we had 10 to the 14th per liter, 10 to the 11th per cubic centimeter, 10 to the 10th, and 10 to the 9th. Well, if these guys would stick, the half-time would be 2 seconds, 20 seconds, and 200 seconds. And that suggests either the generation rates are enormous, which is not likely, or these particles are very stable kinetically in a colloid chemical sense. So we're forming the fertile valley for civilization by unstable particles, and we've got all these stable particles all over the place. And so I wanted to talk a little bit about why these guys are stable or not stable. We're going to start with inorganic systems and the DLVO that Gary raised in his talk. And these are a couple of old pictures of the interface. This is the Gooey-Chapman model. Where we have particles with charges, and they surround themselves with particles of opposite charge. The Gooey-Chapman model winds up in many, 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 many other models. It's a component of lots of other stuff. But it has a couple of assumptions that cause it some difficulties. The first is that there's no chemistry in the model. It's used in lots of chemistry models, but lithium, sodium, potassium, and cesium are all the same in this model. We'll talk a little bit about that later. Calcium and magnesium are the same. It's not a chemical model. And we're going to like to call it a physical model, and we used to say, oh, you're overstating the case. But there isn't any chemistry in the Gooey-Chapman model. And the second is that everything is a point charge. And so especially when you get in close, what we call the excluded volume effect turns out to be a problem. So it's a physical model where things don't have any size, and it's used, but by all, well, I can't say by all of us, but by many, many people, including myself. The other end is this chemical model. This would be some oxide. There is an inosphere layer and an outer sphere layer. Jim Davis worked a lot on this. And chemistry makes a difference here. Phosphate is different than fluoride. Sodium is, well, let's say chloride is different than fluoride. But in order to use this model, there is still some kind of an electrostatic piece of the action that has to be used, because many of these guys are charged. And so this chemical model is just about always married to some kind of a physical model, something like the DLVO model. A chemical model, lots of good chemistry, not great physics in my view. Physical model, no chemistry whatsoever. These are what we use. There are modifications and quote-unquote improvements that have been used by people that study aggregation in order to make some sense out of why we have stable colloids someplace and unstable colloids someplace else. Okay, DLVO model, straightforward calculations, some assumptions. I can laugh at myself. Particle radius 50 nanometers, surface potentials, ionic strength moderately high. You need to talk about a Hammaker constant for the attractive interaction between these guys. It's 25 degrees. This is what you come up with. You have an attractive curve, excuse me, you have an attractive curve from the van der Waals interaction, and you have a repulsive curve because of the interaction of these layers that we usually use Gooey-Chapman to describe. And we have a net interaction, which in this case shows there's a region around 5 nanometers of separation where it's attractive. We call this a secondary minimum. And then there's a region, maybe here about 1 or to 2 nanometers, where there's a repulsive energy barrier. And then very close, there's a primary well at a nanometer or less. This is a typical curve for these kinds of conditions. This is not the strongest laser I've ever seen, I guess. Okay. Well, this is all DLVO. These are 4 different simulations for 4 different particle sizes. 30 nanometers, 100 nanometers, 300 nanometers, and 1,000 nanometers. And the curves on here are just DLVO calculations like I showed you on the last graph. And it turns out that all of these interactions scale directly with particle size. You'll find that in the literature, but it seems to be hiding from a lot of us. For this one, there's a primary minimum of around 1 kT, an energy barrier of around 3 kT, and then there's this well. You multiply the particle size by something like 3, this whole curve is just multiplied by 3. This goes down to about 3 nanometers, this goes up to about 9. What that means is that a particle that gets in here has got to get over 12 kT. A particle that gets in here only has to get over 4. As the particles get larger, this is 90 kT, this is 30 kT. Particles that come in here, if they're going to think the LVO is right, are going to have to get over 120 kT barrier. Not likely. Okay, now what all these dots represent is the closest approach of a particle that was allowed to bounce around by Brownian diffusion. 1,000 particles, something like 100,000 bounces. And we find for the small particle, where the energy barrier is 1 plus 3 or 4 kT, just about all of the particles, after all of these bounces, are able to get over the barrier. So we would call that a theoretical sticking probability of pretty close to 1. And when we make experiments, we actually get experiments pretty close to 1. Okay, here we find that only 6 of them get over the barrier, and about 500 get caught in the secondary minimum, and the rest are in here. And so we would say that there's a primary minimum alpha of 0.006, and there's a total sticking probability of about 0.5. Down here, they're all in the secondary minimum, and so the alpha is 1, theoretically, and if you make experiments, it turns out it's about 1. But the reversibility of this deposition is entirely different. These guys we think are permanently deposited. These guys we think are reversibly deposited. When you make experiments, you'll find that they all seem to be removed, for example, in porous media. But whether or not they can come off again is much different. Well, this is just another, sorry. Well, these are some experiments that Menny Ellie-Melech made at Hopkins with packed beds. I pass some particles in. I pass some particles in. You see what comes out, and you say what the difference is, was removed and retained. Pretty simple and experiment. what we then use is something called the interaction force boundary layer model, which winds up assuming that the particles attach in the primary well. I'm going the wrong way, guys. Okay, this winds up assuming that they go in the primary well. Now, this is KCl concentration, and that's probably a backwards way to look at it. This is 1 molar, 10 to the minus 2 molar. When you think they're going to have to go over the energy barrier, you wind up calculating alphas of 10 to the minus 20, 10 to the minus 50. Theoretical alphas with DLVO, just not possible. You make experiments, you wind up with alphas from 1 to about 10 to the minus 2, 10 to the minus 3. So we say, doesn't work. And lots of people have come up with a whole host of ideas about why the experiments look like this and the DLVO model looks like this. Our approach is maybe a little bit different than some. We say, okay, we've got this secondary minimum. And back in 1859, there was a physicist by the name of William Clarke Maxwell who developed an equation for the kinetic energy or the velocity of particles. And this is just a Maxwell distribution. Fraction of particles with a given velocity goes like this. And we said, well, we've got this secondary minimum interaction energy, and particles need a particular activation energy to be able to bounce themselves out. So if we know what this is, we can calculate what this is, and then we can calculate an experimental alpha, or theoretical alpha, where we're looking at deposition of the secondary minimum being included. Looks like this. And when we do that, for some of the data that we have, not for all the data, we only show you the data for some. This is some of those experimental data I showed you before, and this is for particles that are 46 nanometers. And this is the interaction force boundary layer, and this is the Maxwell model. We calculated it for 2 different Hammaker constants. But one can argue that this, if I can say agreement, supports the idea that the particles are deposited in the secondary minimum and therefore reversible easily, and not in a primary well where it's hard to get them out. Now, we also made an experiment or two. These are packed column experiments. We have some particles coming in. This is what's leaving divided by what's entering. We had 3 different phases in the experiment. These are latex particles. They're being added, and a certain amount is removed. The difference between here and here is what's removed. The red is a 10th molar KCl. This is what that graph was calculated for. And the squares are 0.2 molar calcium chloride, where the 2 seems to have wandered a bit. We calculate that this system would have no barrier and everything would go into the primary well. But remember, for these cases, the alpha is experimental, will look a lot alike. And so the depositions are about a lot alike. Then we shut off the particles but keep the water going at the same solution concentration. And this is what is largely what's washed out of the pores. And then we put some demineralized water in, slightly buffered so there's so the pH doesn't vary. And with the KCl, where we thought things should go into a well and not come out, they don't. And with the 10th molar, with the calcium chloride, they don't come out. With the KCl, we recover most of the stuff that's actually deposited. So this difference supports the view that these guys were in a secondary minimum and these guys were in the primary well. I've got a whole series of examples where DLVO doesn't work, and I just want to show you one. Mainly because, well, we go to the chemical engineers, and the chemical engineers deal with slurries, especially Australian chemical engineers that deal with slurries, because it's a country of mining. And these are experiments where they measure the viscosity of a suspension as a function of strain rate. This is with silica, which has a zero point of charge of 2, but these experiments are pH 9, where the silica is quite negatively charged. You have to have a fair number of solids. The solids volume concentration here is 0.15, and it's got to be monodispersed in order for the theory to work. Okay, in the absence of any salt, where the negatively charged silica has got long-range repulsive interactions, the viscosity is not dependent upon strain rate. When you add salt, I think these all are all for about 0.1 molar of lithium, sodium, potassium, or cesium chloride. You wind up screening the repulsive interaction and allow the particles to get closer together, and there will be more of an attractive interaction. And so the viscosity becomes a function of the strain rate. You have to break that attractive interaction. There's about an order of magnitude difference among the 4 salts depending upon the cation. These are not point charges, and also some of them are heavily hydrated and some less hydrated. So all through this region there is some kind of attractive interaction between these particles despite their negative charge. There are a variety of explanations for that. The simplest one, there have been experiments with the surface force apparatus which show that the interaction as they get close together depends upon cesium, cadmium, lithium, and sodium and lithium, but that the cesium gives the largest attractive interaction because they get closer together. And in the case of the silica with the viscosity experiments, the idea is that the cesium gives the weakest interaction because it keeps them further apart. And the reason proposed for that is that mica is less hydrated than silica, and so lithium can't penetrate very far towards the mica surface, but it can really bury itself near the silica surface. So these guys are kept apart with cesium, and these guys get closer together with cesium. Well, what I want you to think about here is that DLVO is pretty good at relatively long separation distances, and it's hopeless at very close separation distances like a nanometer or 2 or 3. Okay? It just does not characterize the kind of interactions that are there. The organic systems. Old experiment. These are hematite particles, about 70 nanometers in size. Some aggregation experiments, not deposition experiments, at pH 6.3. At 2 ionic strengths, 10 to the minus 3 and 10 to the minus 1. This curve is 10 to the minus 3. And this is DOC added. At these low concentrations, we could never measure what was remaining, so we could calculate absorption. This is just DOC added in milligrams per liter. And for the positively charged hematite at 6.3 and 10 to the minus 3, when we're adding small amounts of DOC, we wind up adsorbing organic matter and neutralizing charge. And this is about 20 micrograms per liter of this natural organic matter. Well, I should say natural organic carbon. But when we add a little bit more, maybe go up to 30 or 40, we restabilize the hematite. We've absorbed negatively charged stuff on positively charged stuff. We've over-absorbed it, and we wind up restabilizing it. If we do the same thing in, sort of in my mind, moving down into an estuary, maybe 0.1 molar, hematite is unstable in 0.1 molar. We're adding organic matter. It's absorbing, it's reversing the charge and making the hematite negative at 0.2 milligrams per liter. Okay? Very, very low concentrations of natural organic matter. As I recall, this is from the Dismal Swamp in Virginia. I put on here just a ballpark range of the DOC in natural waters from about a half a milligram per liter up to 20 or so. And one thing you can infer from this is that all the particles that are out there are going to be interacted with and likely coated with natural organic matter, and that the bare mineral surfaces don't have anything to do with their stability. Okay, a model. This is a model that the Dutch developed. Verwey and Overbeck were Dutch, and this is the Schortjen's Fleer model. It's for linear macromolecules, of which one can argue that maybe humic acid is not one, but the idea is that this looks at the adsorption of linear polymers on surfaces. And it turns out that just about every macromolecule adsorbs on just about every surface. Slight exaggeration there. But macromolecules adsorb on surfaces. The model has got a few pieces in it. It looks at the configurational entropy of the polymer in solution and on adsorption, and it turns out that they lose configurational entropy. So entropically, even though they're all adsorbing, that's unfavorable. There are a variety of electrostatic interactions. If there are charges on the segments, then there's intramolecular repulsion that will tend to stretch them out, and similarly when they're adsorbed. If the segments are of the same charge as the adsorbent, then there'll be an electrostatic repulsion between the adsorbent and the segments. And then after the molecules are adsorbed, if they're all negatively charged, they'll repel each other laterally. And so there's all kinds of electrostatic repulsions and some electrostatic attractions in the adsorption of polymers and interfaces. There's also the issue, do the polymer segments like the solvent, in our case water? What's the Flory-Huggins parameter for them? And depending upon that, the water may be sending them to the surface or keeping them in solution. What the Dutch did was to say, well, in many cases when you look at all of these things, they shouldn't adsorb. And so there's very likely some kind of an interaction between the segments of the polymer and the sites on the surface. And there are models for each of these things, except for the last one. And so this turns out to be a fitting parameter in this Dutch model for the adsorption of polymers on surfaces. Something like specific adsorption energies. Well, being what we call a stomach, we said, well, all these sites are different. There's got to be different speciation of the sites. Excuse me, all the segments have to be different. And also, the sites, very likely, they're not all the same. Some are positively charged, some negatively charged, etc. And so we looked at the possibility of this adsorption being some function of the site distribution on the polymer and the segment distribution on the polymer and the site distribution on the surface. And so we added some reactions like this. The reason for this is that it turns out that in many cases, negative polymers adsorb on negative surfaces. Natural organic matter is largely negative. Many of the natural surfaces, even without the organic matter, are negative, and yet there is adsorption. So these are just calculations. This would be the charge on. Okay, this would be the charge on hematite. Positive above the 0 point of charge, negative below. This is the charge on our natural organic matter. And for the case that we've done here, we just added these two, and this is what we calculate to be the net charge on the hematite that has adsorbed natural organic matter for the amount of stuff we throw in. And it turns out it's negatively charged pretty much down to pH 4 or so. Based on electrophoretic mobility measurements, which I don't trust, the mixture was always negative. Maybe this will be the last one. Let me look at the bottom. With this model, we can calculate the volume fraction of the polymer as a function of distance from the surface. And this is the bulk here. As a function of ionic strength, we have 0.01 molar and 0.2 molar. This is the volume fraction of the tails that stick out into solution. And it turns out that at high ionic strength, there are more tails sticking further out than at low ionic strength. This suggests that the stability as impacted by the adsorbed materials will be greater at high ionic strength in the ocean than it will be at low ionic strength in Lake Erie. Okay. I want to go through some speculations about those cases that we talked about. Start with the Grimsel colloids. High concentration. Very likely inorganic colloids, we give them what we call intermediate Hammaker constant. They're very small, so they probably don't have a secondary minimum. The pH was about 10. And the low ionic strength, so very thick diffuse layer, and low DOC. So these colloids are not going to get very close together, even with DLVO. We say they're stabilized electrostatically by the surface charge. It may be something like a classic DLVO case. There's no deposition, and very likely a possible extension to the aquifer. We go in the ocean. Significant particle concentrations, apparently stable, very likely a mixture of organic and inorganic particles, variable dissolved organic carbon. I'm sorry, we're not in the ocean, we're in the, I can't even read. This is in freshwater systems. Small particles, mixture of particles, variable DOC in the freshwater, low to moderate ionic strength, and variable hardness. The point I want you to take away from here, if you're a DLVO person, it probably doesn't apply to anything that you're studying. The particles are stabilized electrostatically. The stability is reduced by the major divalent cations. The electrostatic stabilization is because of NOM adsorbed in thin layer on the surfaces. Possible deposition aggregation is secondary minimum. And that'll vary with the kind of colloid and its size, with solution chemistry, particularly dissolved organic carbon and hardness. Since it's a great variation in these properties, there's going to be a great variation in stability, and DLVO won't help you. Estuaries. Particles can apparently be stabilized in an estuary. That's how the Nile Delta was formed. A mixture of kinds of particles, variable DOC, higher at the freshwater inlet than at the marine outlet, systematically varying ionic strength, systematically varying calcium, magnesium. Particles stable at the inlet, unstable at some location in the estuary, Some may be stable at the outlet. DLVO doesn't apply anywhere. Stability at the inlet may be similar to rivers and lakes due to negatively charged NOM. Stability at the outlet similar to the ocean, which is electrospheric. I guess I haven't come to that. The instability within the estuary is due to electrostatic screening of the surface charge. Possible aggregation and secondary minimum within the estuary. I guess I skipped the ocean. Let me go back because I like the ocean. Although I get seasick almost every time I go out. Look, ocean. Significant particle concentrations. Many organic colloids, which don't have much of a Hamilton constant. Negatively charged, small size, so small secondary minimum. pH 8, more or less. Probably high ionic strength and high divalent metals, low to moderate DOC. DLVO will not apply. The absorbed NOM contributes to a negative charge with possible thick adsorbed layers, something called electrospheric stabilization. Remember I said that those tails stick out further at high ionic strength than they do at low ionic strength. Possible weak reversible aggregation in a secondary minimum. This piggyback approach was first proposed by Peter Sanchi. The idea is you have big particles and small particles, and they aggregate in secondary minima, and they settle. And then because it's reversible, they separate, and the little ones stay behind, and the big ones keep going until another big one comes along, leaving a lot of small particles, and the big ones disappearing. Okay, this is just one slide of conclusions. Speciation, he says. I'm not going to show that one. Speciation impacts and can dominate aquatic chemistry and aquasol stability. This is aquafacial speciation. Polyelectrolytes, natural and synthetic, adsorb at most interfaces and determine surface charge on particles in these systems. Reversible deposition and aggregation are more common than might be expected. This may be related to very short-range interactions and can be impacted by counter-ion chemistry. Think calcium ions. So think calcium ions, think DOC, and recognize that we don't know much about the first few nanometers at an aquaphase. I do have a slide that didn't make it here of thanks. I thank mentors first, and that's Werner and Don O'Connor and another gentleman named Jack Borchard. Thank students. Jerry mentioned that I've had some good students. I've had some great students, and those students are responsible for all of the stuff, without exaggeration. Thank funding agencies, but there haven't been enough funding agencies. And thank you for your attention.
We have time for maybe one quick question. Charlie, on your, I really like the last few slides where you go from the latex beads to the rivers to the estuaries to the oceans. Have you published any of that with examples? And if not, I'd like to invite you to write a feature article in ES&T.
Well, it's up here, and I've got some other things I'm writing, but I'll put it into the mix. Okay?
Thank you very much.
Can how many people like DLVO? Raise your hand.
We're not supposed to after that presentation.
How many people don't like the DLVO? Raise your hand. How many people slept through the whole talk? Thank you.
We're going to switch from particles in the water to particles in the air. And I'm